Okie dokie, so we are going to be drawing a ray diagram to help us visualize the math that we're going to do in this problem. So the situation here is that we've got a concave spherical mirror, which actually, let me go ahead and show you that. It looks like this. Okay, if you notice how this mirror kind of is bowl shaped, okay, we're going to be looking at the inside surface of that as our concave mirror. Okay, now this one does not have a very really intense curve, so its actual radius of curvature is pretty large here, but this is just a good example to show you. So alright, so here we've got a concave spherical mirror that has a focal length of 10 centimeters, which means that we've got a focal length of 10 centimeters. We want to locate the image of a pencil placed upright 30 centimeters away. So the distance of our object is going to be 30 centimeters in front of the mirror. We want to find the location of the image, so DI, and we also want to find the magnification of the mirror. Alright, so I drew us a picture to kind of visualize what's going on. Okay. Here I do have my concave mirror where the side that my object is on is the reflective surface. Okay. I've got that our focal length is 10 centimeters, which means my focal point will be at 10 centimeters. And I know that my radius of curvature, or my point C here, is twice my focal length. Okay, so this is the same distance here. So this should be at 20 centimeters. And I've got my distance of my object. This is supposed to be a pencil, but I like to draw an arrow so that way I know this way is up. And that's at my 30 centimeter mark. Okay, now this is drawn to scale, but not actually drawn 10 centimeters in each spot. It's actually the only protractor I have right now that I could use as a compass is only allows me to measure in inches. So I've got basically every 10 centimeters is 2 inches, but that's just my scale. Alright, so we are going to want to figure out where my image will be located. Okay, first we'll do the math. Okay. And then I will back it up with my ray diagram. So here I've got our two equations that we can use. I've got the mirror equation, which relates my object distance and my image distance to the focal length. Okay. And I also have the magnification of the mirror, which relates the height of my object to the height of the image formed, and also can relate those heights or the magnification to the distances of the object and the image. Okay, which means first I have to find information using this equation. So in the mirror equation, I know that I have my distance of my object. I also know the focal length, so I can find the distance of my image. Okay, so we've got 1 over DO, or the object distance, plus, 1 over the distance of the image equals 1 over my focal length. Okay. Now a lot of people mess this up, and I'll show you where they mess up. Okay, I know that I want to find DI first. So before we plug anything in, let's go ahead and isolate DI. I can see that 1 over DO is added right now to what I want to isolate, so I'm going to subtract that from both sides. So now I get 1 over my image distance is 1 over my focal length minus 1 over my object distance. Now, this is where people mess up. They usually think that once they've solved the right side of the equation that they have found the image distance. However, this is not the image distance. This is the inverse of it. Okay? So what I'm going to do before I go ahead and isolate this is actually I'm going to go ahead and solve for the inverse of my image distance, and then I'm going to take the inverse. Okay? So let's go ahead and start it from here. So I know that 1 over my focal length of 10 centimeters minus 1 over my object distance of 30 centimeters. Okay, so my 1 over, my image distance, okay, is going to be 1 divided by 10. Hey look, it's just a tenth. That makes a lot of sense. Can you see that? There you go. So 0.1 centimeter minus 1 divided by 30, so 0.033 centimeters. So 1 over my image distance. Okay, so I'm going to take my 0.1 centimeters minus 0.033 centimeters, and I get 0.0671 over centimeters. And those should be inverse, but okay. Alright, so this is 1 over my image distance, so the way that I can isolate the image distance is to raise everything to the -1 power. Okay, or basically take the inverse or take 1 divided by whatever. Okay, so it's going to give me my image distance as, when I do this, I could do two things. Alright, on your calculator you see x to the -1 power, so I could just do that and I should take my answer to the -1 power. I should get 14.9. Or what I could have done, so see how I've got 0.067, I could do 1 divided by 0.067 because it's the same thing as taking the inverse and I get the same answer. Two ways to do it. I like the handy dandy, it takes the inverse for you button, but that's up to you. So now my image distance should be at 14.9 centimeters from the mirror, so it should be beyond my focal point, but not quite at my radius of curvature, because I know my radius of curvature should be 20 centimeters, so it should be somewhere between that center of curvature, that's point C, and point F for my focal point. Okay. We'll check that here in just a second. Alright, let's check the magnification. I'm going to use a different color for magnification. So I know DI now is equal to 14.9 centimeters. Okay, the magnification now, let's do in red. Okay, so for the magnification, I'm going to use the magnification equation. Okay, so I know HI over HO negative DI over DO. Okay, now if I'm just looking for the magnification of the mirror, all I have to do is take the negative image distance divided by the object distance. Let's go ahead and just do that one first. So I'm going to take negative 14.9 centimeters divided by 30 centimeters, excuse me, for my object distance. Okay, so I should get, so negative 14, it should be around a half, but we'll just double check. Yeah, so it's about a half. So negative, actually that 6 is going to round it up anyways, 0.5. Okay, my centimeters cancel. So my magnification says a couple things. That negative means that it's going to be inverted. So negative inverted, which means that my image should be upside down. Okay, this 0.5 is also the ratio of the image height to the object height, which means that my image should be half as big. You could always plug this in to find your image height. Okay, so multiply both sides by your object height. So my image height should be, my magnification is 0.5. I could do negative, and that just is going to, let's go ahead and just do that too. Negative 0.5 times 30. Oops, excuse me. Actually, I did on this one. I did not give an image height. So, actually, scratch all this. But we'll work a problem here. I'm sorry. I thought that I gave you an image height. Let's just refer to the ray diagram and see if we do see something that's about half as big. Okay. All right. So, oops. All right, so for the ray diagram, I've already got this all drawn out to scale. I'm going to draw my 3 reference rays. Okay, the first reference ray, and I like to just start with the very top of my object, and that's going to be the exact same point on my image. My first reference ray is going to be parallel to the principal axis for the incident, and then it's going to reflect off the mirror and bounce off and go through the focal point. And you can get a little bit messed up as far as if you're not 100% on, but it's okay. Alright, so here I've got that reference right here. I'm going to use a different color for each reference ray for right now, so you can kind of keep up with what I'm doing. The second reference ray is going to go kind of opposite of what you just did. It'll go through the focal point first and then reflect parallel to the axis. Okay, so now let's go parallel to that principal axis. Okay, and then let's use purple now for the next one. Okay, the third, excuse me, reference ray is going to start at the same point, and this time it's going to go through the center of curvature and then bounce back off the mirror and reflect back onto itself. Okay, so let's try to get that all lined up. So it goes through the center of curvature and then bounces back on itself. And you should notice how right here we get an intersection of all three lines. Okay, this intersection is going to be the exact same point on our image as it was on the object. Now, that was the tip of the arrow, so this is going to be the tip of the arrow. Okay, and if you notice, that is roughly about half as big. It is upside down, and it is approximately halfway to the object. So our ray diagram does confirm our math. All right, I'm just going to review our numbers that we calculated and show you how they fit onto here. Okay, we measured that our image distance should be roughly 15 centimeters. Okay, well, we know that this is 10 centimeters, that's 20. That's roughly halfway in between, so that works out. Okay, and we also calculated our magnification to be negative 0.5, which means that it is inverted, or upside down, excuse me, I didn't mean to hit the camera, upside down, and it should be about half as big as my image, or my object, and it is. So, yay for happy ray diagrams.